Hello, I'm Mike McCulloch. Today I'd like to talk about Galileo's rainstorm. So, about 2,000 years before the time of Galileo, or a bit less, Aristotle had said that heavier bodies fall more rapidly than small ones, and this had been accepted for nearly 2,000 years. But when he was quite young, Galileo witnessed a hailstorm, and he noted that the small hailstones hit the ground at about the same time as the larger ones. And so if they'd been formed at the same height, you would expect, if Aristotle was right, the larger ones to hit the ground first, and then you get a lighter hail after that. But that didn't seem to be the case. And in fact, Galileo also saw a piece of wood falling, which seemed to fall about the same rate as the hailstones. So this led him to challenge Aristotle's proposal that heavier bodies fall faster, by saying that all bodies fall at the same rate. And that's because although heavier bodies have more gravitational mass, so are attracted more, they also have more inertial mass, so they are slower to accelerate. But Galileo's contemporaries were very fond of Aristotle, and they didn't like it that Aristotle's theory was being challenged, as these things go. That is the way these things go. So they came up with an ingenious rebuttal to Galileo in saying that the larger hailstones hit the ground at the same time as the smaller hailstones because they were being formed higher up in the atmosphere. So this was quite a clever way to argue, because nobody at that time could get up into the atmosphere to observe what was actually going on, so they were perfectly safe in arguing that, and it left Galileo quite frustrated. And I have to say I quite sympathise with him, because something very similar is happening in physics today. So our current model of gravity, general relativity, failed to predict almost every galaxy ever seen. Their rotation, it failed to predict their rotation to a huge degree. But instead of considering a reformulation of the theory, most astrophysicists have invented a new observation, dark matter, which they add to galaxies to bind them together, to keep them bound even though they're spinning so fast. And they have to add far more dark matter than is visible matter in the galaxy. Now, this of course is a way to do it, but you notice that just like in Galileo's time, they do not give a reason for this dark matter. They do not give a model for it. It can't be tested. It's never been seen, even after 40 years of looking. And they're quite safe. They're quite safe in proposing it, because it's extremely difficult to falsify, although it can actually be falsified, and it has been. It is quite a tricky thing to do. So I hope you can see the parallels between that time and this. And it's also interesting that there are other parallels as well, because it was Galileo's formulation of the equivalence principle, the equivalence between gravitational mass and inertial mass, that led to his revolution. And what quantized inertia does in this day is to actually challenge that, to slightly modify it, to say that the equivalence principle is not quite right. There's a very tiny difference in that the inertial mass is not quite linked rigidly to the gravitational one. There's a slight difference, but it is a slight difference that would not affect, there's independent of mass. So if Galileo dropped two balls of different weight from the Tower of Pisa, with quantized inertia they would still fall together, but they would both fall slightly faster. Okay, so I hope you've enjoyed this short, and I look forward to seeing you next time. Goodbye.